Assalamu alaikum warahmatullahi wabarakatuh. Welcome to another computer science lecture for 9618A2, paper number 3, Advanced Theory, and we were doing chapter number 15, Hardware and Virtual Machine. In our last lecture, we took care of 15.1. Now it's time to discuss 15.2, Boolean Algebra and Logic Circuit. Okay, so basically, the first thing we have over here in this chapter is known as half adders and full adders. Complex logic gates are those logic gates that involve logic gates which take more than two inputs. Normally in your AS in O levels you only went through logic circuits that could hold up to a maximum of two inputs. But there are complex logic gates in real life that can take 3, 4, 5, 10, 9 inputs easily. This leads to an exponential increase in possible input combinations, and they require a thorough understanding to interpret the larger truth tables. So among those complex logic circuits, we have two things: half adders and full adder circuits. Adders are specific logic circuits which are used in ALU, arithmetic and logic unit, within the CPU to perform binary addition, hence the name adder. Half adder is a circuit that adds two binary digits and output a sum as well as a carry. As you know, in binary addition, if you add two ones together, you have a 0 as an answer and 1 as carry. It consists of a XOR gate for summing functionality and an AND gate for the carry. The truth table looks something like this. It has an A input, a B input, because only two digits can be summed, then a sum output and a carry output. So if both of them are 0, sum is 0, carry is 0. If it is 0, 1 or 1, 0, sum is 1, because 0 plus 1 or 1 plus 0 is 1, but there is no carry. However, in case of 1 and a 1, so 1 plus 1 is 0 is the sum and 1 is the carry. For the sum column, output is consistent with the XOR gate, whereas for carry column, it is consistent with an AND gate operation. A and B would result in a carry, A XOR B would result in this sum column. Half adder has only two inputs and there is no provision to add a carry coming from the lower order bits when multi addition is performed. That's why we have a full adder. Anyways, this is what a half adder circuit looks like. If you're trying to add multiple bits or two bytes together where you have to perform addition operation on multiple bits, for that we use a full adder. It can add 3 binary digits including the carry from a previous addition. It combines two half adders and an OR gate for the carry output. The truth table looks something like this. We have A, we have a B, and we have a carry input. These three are the inputs, then sum and carry is produced as an output. This is how we write it: A XOR B XOR CI for sum, or for carry output we can write A dot B or CI carry input A XOR B. This is what the circuit looks like. A full adder circuit looks like. We have two half adders, this one and this one, joined by an OR gate. Sequential logic circuits. Sequential circuits are digital circuits that store and use the previous state information in order to determine their next stage. You can say they kind of use the previous calculation in order to determine the answer of the next calculation. Unlike combinational circuits, which can only depend on the current input, sequential circuits depend on both the current input as well as the previous state stored in the memory. The examples of such circuits include flip-flop circuits. Flip-flop circuits are special circuits that are very common in electronics and computers. This is what a sequential circuit looks like. It uses a combinational circuit along with a memory element in order to calculate something that can use the previously saved state in its next output. A flip-flop is a bistable device. That means it has two stable states which allow it to store a single bit of binary data. Technically, if you remember, your SSDs and a lot of registers inside your computer are made up of flip-flops. The characteristic is utilized in various digital applications such as memory storage, data transfer, and timing operations. Now we have many types of flip-flops, and we are not talking about the sandals. I guess some types of shoes are also known as flip-flops. Anyways, there are 4 or 5, I think. There are many types of flip-flops. However, in our syllabus we only have 2 types of flip-flops: the SR flip-flops, and the next one are supposed to be the JK flip-flops. These are the only ones we have in our syllabus. So the SR flip-flop circuit looks something like this. It is made up of 4 NAND gates, and traditionally in electronics we usually draw it like this. It is one of the most simplest types of circuit, consisting of 2 inputs, a set and a reset, as well as 2 outputs, typically labeled as Q and Q bar or Q complement. This is the clock signal. This is it is an input, but it is generated automatically. Let me fix. Okay. When you activate the set input, which is also known as the high signal, it sets the flip-flop, turning the Q output 1 and Q bar as 0. When you activate the reset input, like this is the reset input, whenever we have a 1 over here, then the output is reversed. Q becomes 0 and Q bar becomes high. When both S and R are low, 0 or low, the flip-flop retains its previous state. So if you have a 0 on both S and R, you'll retain the previous state. If you have 1 over here, 0 over here, it will be 1 0, otherwise it will be flipped. The truth table for a flip-flop is like this. When S and R both are 0, Q and Q bar are also 0, and this is what the truth table for a SR flip-flop looks like. You'll kind of have to learn these outputs. They are not really traditional outputs. Like if given in the exam, you probably won't be able to solve them in time. So it's just better to learn the outputs. Remember that the Qn plus 1 or Q bar column, the last 2 states over there is not applicable. So we just write a dash over there. Then we have the JK flip-flop. It is an advancement over the SR flip-flop, which is designed to overcome the ambiguity of SR flip-flop when both inputs are high, if both inputs are 1. The circuit looks something like this. Sometimes it can be made up of NOR gates as well instead of NAND gates, but they kind of do the same thing. As long as it is a JK flip-flop, similarly instead of NAND gates, it can also be made up of NOR gates, but that doesn't really make any difference. The JK flip-flop changes its states based on the J input or the set input and the K input or the reset input. Clock remains same. So these 3 are the inputs, and Q and Q bar are again the output. A unique feature of JK flip-flop is when both J and K inputs are high, the flip-flop toggles its state. Whatever was its previous state, if it was 0, it becomes 1. If it was 1, it becomes 0. The truth table for it looks something like this. Again, it's better to just learn, like the J, K and Q. Q is for your clock. Not really for your clock, but the Q is included in your input. 0 1 0 1 0 1 0 1, then 0 0 1 1 0 0 1 1, the standard 3 inputs, and this would be your output. just learn it up, because we don't really have a logic equation that you can apply then and there in your exam to find the output. Flip-flops are vital in digital circuits for a variety of functions. They are used for data storage, as they are used as basic storage units because they can either store a 0 or a 1. They are used in clocking and timing operations as they change their state on arrival of a clock signal. So they are very crucial in timing applications. Shift registers and counters, they are key in creating data shifting or data counters, like something that counts down to a 0 or something that counts time or seconds. Memory elements, flip-flops serve as the foundational building block for complex memory structures, including registers and memory array. Okay. Next we have the Boolean algebra. You're going to, again, you're from this topic, you're going to have at least one question in every paper 3. There are two methods in a logic function, that basically two methods that we use when we are converting a truth table into a logic circuit or into a logic expression, that namely sum of product and product of sum that you have discussed, that we have discussed in chapter number 10 of O levels as well as in AS as well. These are the ways to represent the reduced logic function. They can be used for designing a logic circuit. The prior difference between them is that SOP contains the OR of multiple AND gates, whereas product of sum contains one AND gate, or basically AND gate between the brackets, and inside the bracket we use multiple OR gates. Boolean algebra is a form of mathematics that deals with the statements and their Boolean values. If you remember, when you convert a logic truth table into a logic expression, it is usually quite long. It looks something like or I should just use OR. Oh, I'm using dots, so yeah, let's just go ahead with that. This can be very complex to draw, although it is this would be considered as a very good deduction of a logic statement or a logic circuit just from a truth table, but drawing it would be complex. For that we have Boolean logic. If you remember, in O levels and in AS, it is clearly written on top of logic gate questions, do not try to simplify the logic expression. That is where Boolean algebra steps in. Boolean algebra, by using Boolean algebra, you can simplify the logic, the expression, and you can reduce it to fewer terms. As you know, Boolean operators are carried out in this order: not has the highest priority, and has the middle priority, or has the lowest priority. However, we refer them as symbols. Use dot for AND, plus for OR, and a bar for NOT. Here are some rules for Boolean logic that you should really learn, because they will come very much handy when you're trying to solve Boolean algebra questions in your paper 3. We have a commutative law that says A plus B is equals to B plus A, or for AND gate, A multiplied by B is always equal to B multiplied by A. Then we have the associative law that says if you have A plus bracket B plus C is same as A plus B bracket plus C. If you are adding three inputs together, then regardless of on whichever two you put the bracket, the result will be same. Same is the situation with the AND gate. A multiplied by B dot C or AB multiplied by C outside the bracket, both of them will have this exact same answer or exact same output. Then we have the distributive law. A dot B plus C would be equal to A plus B. Basically, we are opening the bracket. A is multiplied by B, so it becomes AB plus A is multiplied by C, it becomes AC. Similarly, A plus B multiplied by A plus C will be equal to A plus BC. You can solve it out yourself. And A plus BC is equal to A plus B multiplied by A plus C. This is basically just simplifying the bracket. Tautology or idempotent law. A dot A is always equal to A. If you multiply or add A with itself, you'll always get that input back. Like C dot C should be just written as C, or B plus B should be written as a single B. Now these laws will really come in handy when you're trying to simplify your logic expressions. Often in paper 3 you'll be given a long logic expression and you'll be asked to simplify it. Over there all of these laws will come in handy. Then we have the identity law, 1 multiplied by A or 0 plus A. Like if you have any input and you add 0 to it or you multiply it with 1, you'll get the same input back. Null law means if you multiply any value, any input with 0, or you add 1 to any value, it will if you multiply any input with 0, it will become 0, whereas if you add 1 to any input, it will become 1, regardless of whatever is the value of that input. Then we have the inverse law. Any input multiplied by its complement will become a 0, and any input plus its complement will always be a 1. A plus A bar will always be a 1. So if you're given a long equation, if it has A and A bar or B and B bar or C and C bar, you can just cancel them out and write them as 1. Absorption law says that A multiplied by A plus B would ultimately be equal to A. You don't have to write it as A plus BC. Sorry, you do. Sorry. Yeah, A multiplied by A plus B, because would be equal to A. Similarly, A plus AB would also be equal to A. A plus AB, A plus A bar B would be equal to AB. Finally, we have the De Morgan's law. A dot B whole bar means if there's an AND gate between A and B would be equal to A naught plus B naught. Similarly, A nor B can be opened up as A bar and B bar. A visual representative is shown below. Both of them are equal, regardless, both of them are equal as well. This or this will always have the same output. Again, with the AND gates, it will also have the same output. If you have one OR gate and one AND gate, or you have two AND gates and one OR gate, in this situation you'll always have the same output. Solve the example simplifying a logic circuit or expression. Consider the following logic circuit for simplification. So first of all, you can see A and B, then you can go for B or C, then AND B and D, B and C, and ultimately between all of them we have an OR gate. So Q, that's your final output, will be equal to A and B, the first part, then plus B plus C, the second gate, and the output of this gate will go into an AND gate with this sequence B and C, and ultimately between these two brackets, this and this expression will have an OR gate over here. Now that we have a Boolean expression to work with, you can apply the rules of Boolean algebra to reduce the expression into its simplest form to a point where you cannot simplify it any further. So first of all of this can be written like this as well, there's no problem. Using the distributive law, as we have studied over here, this is the distributive law, A multiplied by B plus C. Do we have a situation like that? We have it would become AB plus BBC, because by using the distributive law we are basically opening the bracket first, we are expanding the bracket. So it would become, this AB would remain same, this OR gate would remain, or plus would remain same, this BC would be multiplied by this B, it becomes BBC, this BC would be multiplied by C, becoming BCC. Now you can apply this law, idempotent law. Any input multiplied by itself is a single input. Any input added by itself is also that input. Over here we have two instances. We have B multiplied by B, so we can just write 1B for it. Similarly, over here we have C multiplied by C, so we can write just 1C over here. So it becomes AB plus BC plus BC. Next we apply the idempotent law for the OR gate. Any number added with itself will return that number. So AB plus BC would simply become AB plus BC. One of them can be cancelled out. Now you can simply use the rule of factorization to simplify it further. B is common, keep it outside and put A plus C inside, and that's it. Now as you can see, drawing this or making a truth table of this is a much bigger task as compared to simply drawing or solving this. I have another example as well. A plus B, A plus C plus AC. Now you can use the distributive law, open it up, so it becomes A plus AB plus BC plus AC. Now use the absorption law, so it becomes A plus A would simply become an A plus AB would simply become an A, plus BC plus AC would remain same. Next you can use the absorption law again. A plus AC would simply remain as A, and this plus BC would remain same, so it becomes A plus BC. You can apply both of them in a single go as well. Over here I use them in two different steps just to make you understand what is happening in the background. If I had, after this step, if I had just made it into simply A plus BC, you would have been slightly confused that what happened to, how did these four terms become just two terms. And well, technically we can't really simplify it any further. A is distinctive, B is distinctive, C is distinctive as well. So that would be our final answer. Next we have something, a very useful tool for solving Boolean algebra, that is known as K-maps or Carnot maps. They are a tool to represent and simplify logic expression of up to 6 variables. A K-map can have more than 6 variables, but it would be too complex if not impossible. A K-map or Carnot map can be thought of as a special version of a truth table that makes it easier for you to simplify Boolean expression. It is best suited for functions with 2 to 4 variables. They can be used for functions with 5 or 6 variables as well, although it is much difficult, and above 6, well, okay, let's just agree it would be next to impossible. Using K-maps for functions with 7 or more variables is extremely difficult. Like, you probably would not be able to do so on your own. You'll probably have to make a computer fill in for you, or unless you're a math genius. Rules of minimization is in K-map, like how you can fill in a K-map and how can you simplify the expression using a K-map. Basically you are going to need a truth table, and basically you fill in the given grid. K-map is always in form of a grid that can look something like this, and then after filling it up you make groups that would contain an even number of ones by using your pen or pencil. You can either make group of ones or by zeros, but not both. Like, whatever group you make, it must contain all zeros or all ones, but not a mix of both. Grouping of ones lead to sum of product, grouping of zeros lead to product of sum. While grouping, the group of ones should not contain any 0 and zeros should not contain any 1 and so on. The function output for zeros should be complemented as f complement, whereas for ones it should be simply f. Groups can be made vertically and horizontally but not diagonally. Groups made should be as large as possible even if they overlap. All the like terms should be in a group even if they overlap. Uppermost and lowermost squares can be made into a group together as they are adjacent. Same goes for the corner squares. Each group represents a term in Boolean expression. Larger the group, smaller and simpler the term. The product of those literals that remain unchanged in a single group makes the term of the expression. Absolutely no need to worry if you don't understand these boring rules. Let's just look at a live example. Now, if you have two variables, the K-map, you will have a trace truth table like this, and then you can convert it into a K-map like this. The first output or the first line of your truth table will be written in this position. You can call it as 0 0. The second will be written in 1 0. The third one will be written over here. The fourth one will go over here. As you can see, the first top left corner contains a value of 0 0 from truth table. Like basically this is these two, this is 0 0. So the output of 0 0 is alpha. We write it over there. The next one is 1 0. Sorry, the next one is 0 1 because A is written down. So 0 1, that row is over there. 1 0 is over here and 1 1 is over here. A filled version would look something like this. If this is a trace table, you fill in the first value is 0 is written over here, the second is written over there, third is written over here, fourth is written over here. Now what you need to you need to make groups. Now groups can either contain ones or zeros but not both. Over here we have two ones and two zeros, so I'm going to circle the ones. Yes, you should, and you will be asked to circle them using a pen or a pencil in one of the questions. So yeah, it's totally fine to draw circles or groups on your K-map after filling it up. Now this is the largest group of ones possible. Right now there's just one pair, so circle it and write your answer according to these rules. This row would represent B complement. This row would the first column, if it's highlighted, it would represent B complement. The second column represents B. The first row represents A complement. The second row represents A. Right now we have circled the second column, so that means your answer should simply be B. Hence the final output or simplified version should just be B. Whatever is your B output, as you can see, 0 1 0 1 0 1 0 1, it matches perfectly. You don't need a whole circuit, you can just write B and that's it. Try another version. Over here this is 0, this is 1, this is 1, this is 1. Now as you can see, neither A nor B completely matches with the output. So now there are three ones. That means we can form two groups, because groups cannot be made diagonally. Hence we will be forced to make two groups, one vertical, one horizontal. Groups can either be vertical or horizontal, but they cannot be something like all of this cannot be made into a one group. After you have circled both groups, the first one, this corresponds to A. As you can see, the second row, if it is circled, it would represent A, and the second one you already know, it will correspond to B. Since we are choosing one outputs, we have to go with sum of products, so that means A plus B. If we had made a group of zeros in the similar position, it would be A multiplied by B. But right now, since we are going with one outputs, it will be A plus B. That will be the simplified version of this truth table using K-map. Similarly, if you have a 3 variable K-map, I think this question is from past papers. If I, yeah, this is again for your understanding. You fill in the values. See, this is A, B and C. So that means 0, 0, 0. The first value of X will be written over here, 0, 1, 0, 0, 1, 0. This 0 will be written over here. 0, 0, 1 will be written over here, and so on. Now the biggest groups you can form are this one and this one. Over here you can see both A and B are on. That will be our first group. You can take it as A multiply AB or A dot B, plus for the next one what you need over here, A is missing, so you'll write A complement, B is there, so it will be a B, and C is also there, so it will be A complement, A bar, B and C, plus it will be ABC. Why ABC? This is A, this is B and this is C. This one, just this circle, it has an A, it has a B and it has a C. All three of them are on to give a 1 output. So again we are going with the 1 outputs. We'll put OR gate between these three terms and then we can simplify them further to simply, because AB, over here we have A bar, over here we have A, both of them can cancel each other out. We'll be left with BC plus BC, that can be further simplified to simply BC. You can write it in this form as well if you want. Otherwise, if you just leave it like this, that is also fine, but it's better to factorize it. Most of the time in your paper 3 you'll be given a 3 input table, truth table and a blank K-map like this, which you'll have to fill, and then you'll have to make pairs and you'll have to write the simplified version equation. Reduction of a 4 variable K-map. Here's a example where I have already filled a 4 variable K-map with the values from the truth table. I have not drawn the truth table over here. As you can see, I've got one group over here and I've got one group over here. In this group I have A and B on. So I'll write that. This was basically the final output. For the first one, A and B both are off, as you can see, but C and D is on. For the next one, we have A complement and B is on, C and D is also on. For the third one, for this one, A, B, C, D, all of them are on. Then plus the next one, A is on, B is off, so A, B bar, C and D, both of them are on. Then we go for this line. Over here AB is on but CD is off. Over here then AB is on, C is off and D is on. Over here this one, the overlapping one, we have already written over here, so we'll just go and write the expression. You can say for the last one, A is on, B is on, A is 1, B is 1, then C is 1 but D is off over here. Now you can apply the rules of Boolean algebra you learned above, and ultimately what you are going to get is A dot B plus C dot D. By encircling the largest two possible groups, okay, well, this is basically the explanation of how we get our final answer that I have already explained, but if you like you can read through them. Now if you have a situation where you have one on each corner of your you can say K map, then you can make them into a single group like this. Then you can write values for them. For this one, A and B both are off, C and D are off as well. So A bar, B bar, C bar, D bar. For this one, A is A bar, B bar, C is on, and D bar. For the third one, we have A is on, B is off, C is also off, and D is also off. For the fourth one, A is on, B is off, C is on, D is off. Once we have written our expression, you can write it in rough if you don't have enough lines, and then you can simplify them. And once you have applied the rules of Boolean algebra, then you can simply simplify it to B bar dot D bar, and that's it. As A and A bar would cancel each other out, as well as C and C bar would also cancel each other out, only B bar and D bar would be left. We don't have a B anywhere in the mix, otherwise B bar would have also been cancelled out. We have two A bars and two A's which can cancel each other out. Similarly, we have two C bars and two C's that will cancel each other out, leaving only B bar and D bar. Advantages of K-map: sometimes we get something like a 2-mark question, that what is the advantage of a K-map. This simplification technique is simpler and less error prone as compared to method of solving logical expression by using proper Boolean algebra. It prevents the need to remember each and every Boolean algebraic theorem. However, for your sake of your paper, from the point of view of your paper, you'll need to learn both the things. Unfortunately, you cannot simply simplify expressions by using K-maps until and unless you're told in the question. So typically in a single question from topic 15.2, it will consist of 3 or 4 parts, A, B, C, D, and so on. You'll be using some of the parts you'll be solving using Boolean algebraic theorems, and 1 or 2 of them you'll be solving using the K-map method. K-maps involve fewer steps. It's easier to simplify. K-map simplification techniques always result in a minimum expression, whereas in Boolean algebra you may do some mistake and you may end up having a wrong answer. Limitations or disadvantages: the most significant limitations is that it is only efficient when Boolean expression has less number of inputs or less number of variables. It becomes overcomplicated or very complicated as you increase the number of variables. The simplification of a Boolean function having more than or equal to 5 variables is quite complex, and then 6 is more complex, and 7 and above is, well, almost impossible. So I hope you were able to understand K-maps properly. I've tried to help you out as much as I can. This is absolutely everything you need to know for your chapter number 15. If you have any problems or questions, feel free to write them down in the comments. Give this video a thumbs up if you like it, if you enjoy it, and share it with your friends. I'll see you guys in the next lecture. Till then, take care. Allah Hafiz.